that when the NOx increases following an EPP event, there's a reduction in the concentration of ozone at the same time. Settler et al. Took this even further by considering whether EPP can actually cause changes all the way down to the surface and the temperature there. She found a statistical significant correlation between the geomagnetic activity and the polar surface temperature, where she used the geomagnetic activity as a proxy for the EPP, separating in between high and low EPP. So here we see there are regions which have in these contour plots where the change in the temperature is between plus minus 4.5 Kelvin, implying that EPP can also affect the very surface. This is all very important as we see that because of the effects up in the upper atmosphere, we can see some of these effects all the way, propagate all the way down to the surface. And so the subject for this thesis is going to be the horizontal transport and dynamics of NOx. However, the aim of the thesis is to create a toolbox that will be applicable to single-site studies, to the auroral oval, and through a global perspective. In order to see how we, in order to look at the application of this toolbox, we look at the influences on the effective lifetime of NO and the spatial and temporal evolution of NO. But to get started, we're going to discuss the theory a little bit to see what we're trying to reproduce throughout the thesis. For the production of NOx, there are many different chemical pathways, but this is the way you can break it down. This is the most simple way to look at it. The production of NO consists mainly of this reaction, where inside the nitrogen interacts with molecular oxygen, producing NO and O. This happens through the dissociation of N2, where you have an excited nitrogen as one of the results, and other ion chemistry, which ends up as NO. The main reaction for the reduction of NO is through the photolysis of this reaction, where the ultraviolet spectrum reduces the concentration of NO by photodissociation. This is important as this is what gives NOx a long lifetime in dark conditions, because if it's not a winter solstice, the NOx is not reduced, it's not reduced as efficiently. This means that the lifetime goes from being less than a day in sunlit conditions to several days, weeks, or even months in the right area of the atmosphere and with the right conditions. The reason NOx is important is the fact that it partakes in catalytic cycles reducing the ozone. However, we see that both NOx or NO and HOX partake in this same reaction where you reduce NO. But the reason we emphasize NOx is that HOX has a very short lifetime, which is why it's interesting to look at NOx in terms of the transport. We also have to briefly talk about the energetic particle precipitation, as this is the source of the NO production. Energetic particle precipitation takes many different forms. We have the solar proton events, we have auroral electron precipitation, and we have relativistic electron precipitations. The regions and altitudes they affect varies in between all of these. We see that, for instance, in this figure, that the solar proton makes its way through the magnetosphere by the cusp, so it affects the entire polar cap. While auroral precipitation mainly comes from the plasma sheet at the night side. And the relativistic electron precipitation, it's a bit small there, the relativistic electron precipitation makes its way through from the Van Allen, that's the radiation bands. So, and all of these have different energies, thereby penetrate at different altitudes, and they affect different regions of the atmosphere. Speaking of the atmosphere, we need to look at a bit of the theory around the atmosphere. For the atmosphere, there's these four principles that mainly govern the interaction. You have the Newton's second law, but seeing we're looking at the fluids, it's in the form of Navier-Stokes. We have the conservation of mass, conservation of energy, and then an equation of state, the idea of gas law. These are simple physical principles in practice, but however, in practice, there's some differences because we're on a spherical object. You have to take into consideration, among others, there's the Coriolis force. This is why we have quite strong zonal winds in the stratosphere, as seen here in the subtropical jets. We also have something that seems quite counterintuitive, where this is the summer end of the hemisphere, where you see that the coldest region of Earth is actually in the summer mesosphere, or the summer MLT, while the winter mesosphere, where you don't have any solar exposure, is warmer. In order to understand the climatology, we need to look at atmospheric waves. Atmospheric waves are different perturbations of the physical quantities in the atmosphere, which are on different sizes and scales, where we have, among others, Rossby waves, gravity waves, and tides. And the reason we look at these is in order to understand the meridional transport seen from the summer pole to the winter pole. When you only take into consideration the pressure force and the Coriolis force, they are in an equilibrium, leaving you with the zonal winds. This is what we saw in the jets, where you have strong zonal winds. However, when these different waves propagate up in the atmosphere, for instance, gravity waves can propagate all the way up to the MLT region, where it breaks, deposits momentum, which then imposes a drag on this equilibrium, seen as the F drag component there. This rotates this vector, giving it a slight meridional component, which is seen here. And the result of this is that we have a net flow going up to the winter hemisphere, and through adiabatic compression, it's warming this part of the atmosphere. And that's why you have a very cold summer in mesosphere, as you have adiabatic expansion with the depletion of mass in this region, which is again this transport we're seeing here. This is important as this explains the climatology as we know it, and it also couples the atmosphere vertically, as this is gravity waves originates from the troposphere and propagates all the way up to the MLT. So we can't just ignore the other regions. Okay, so that was a brief introduction to the theory. Now we move on to the method we used for the results here. A brief description is required for the models and data used. We use two different kinds of wind models. The first one is the horizontal wind model series, where we more specifically use HWM07. It's a climatological model in the form of truncated vector spherical harmonics, which is based on 50 years of empirical measurements, both ground-based, rocket sounding, and satellite measurements. And this is a climatological description of the atmosphere. Another model we use is the whole atmosphere chemistry and climate model, WACCM,